Welcome back to Fat Mama Physics. We're continuing with vectors and scalars, and we're going to look at, in this video, how to communicate directions in a vector. So what does it look like in 1D? What does it look like in 2D? And there's a little bit of nuances in the language, so let's get down to it. So we know what a vector is. A vector not only has magnitude, but it also has direction. So in 1D, in this course, you're going to be seeing a lot of 1D and 2D examples. In 1D, usually we would say something like 2 meters west, 3 meters north, south, east, using one of these kind of examples. And this is really looking at, say, a kind of like a bird's eye view. So for example, if I'm looking down on someone walking on, say, a grass field, then I can say this person is walking at 32 kilometers per hour, which is not possible, potentially not possible, north, south, east, west, etc. So it's like a bird's eye view. Okay, so it's in one direction, so relative to a compass or some sort. Okay, so relative to a compass, that's kind of like a bird's eye view. Then you have another view, which is the up and down direction. So for example, if I'm looking at something on the side, then something is either moving up or if it's moving down. Okay, so that's very straightforward. It's in one dimension, so it's along a straight line. Okay. Now the next one is a 2D example. So we're going to be dealing with 2D in a couple examples where we're looking down on something or something is moving, what we call projectile motion. So projectile motion sort of looks like, oh, I throw something at an angle and it follows some sort of parabola shape. That's something we will deal with in this unit, in a 2D projectile motion. So what happens is when we look at something that is moving in projectile motion, oftentimes we are looking at a side view. Okay, so what that means is, okay, I'm going to use some figures to help us visualize this a bit. So if you can't see this, here I have figurines from a board game I enjoy playing a lot, which is Mage Knight. This is Norwas. If you take a look at him, nicely done. Very expensive board game, but totally worth it. Here we have, oh, I should have forgot his name, but he looks like a dragon. I use him for flying purposes. So let's say we have this knight-looking guy here, Norwas, and then you have this dragon. He is, say, flying at a certain angle over into the sky. Then you can kind of see that he is looking at the dragon from a side view. Okay, it's from a side view looking at the dragon. So then when he looks at the dragon is moving at a certain angle relative to what we call the horizontal. So the horizontal, think of it as a horizon. It's sort of like the surface, the flat land. And then he's moving at a specific angle above that horizontal, or he may even move some below that horizontal, some angle below that horizontal. But as a knight, he is looking at this dragon from a side view. So that's what that view looks like. Okay? So let's see what that looks like on paper. Now, let's take an example. I'm just going to write 30 degrees as an arbitrary example and so what that looks like is I have a person standing here. He's doing a side view, and let's say he has, like Nora wants, he sees this dragon flying at him. My terrible attempt at drawing this dragon looks like some bird. Okay, so let's say this dragon is moving in that direction. Okay, so then what that horizontal line is, it's this horizontal line that is parallel with the ground, and 30 degrees would be this one right here, 30 degrees. Okay, so that's what we say when we talk about something that's flying some direction up and down, and some direction side to side. Then we use this kind of language. Okay. Next up, we have the below the horizontal, similar to above the horizontal, except we have this guy, he's looking from the side, Norwas, and this dragon here, oh shoot, he's flying downwards. Okay, very bad drawing. Anyways, he's flying down. He is flying downwards, let's say like this. He's doing a nosedive, maybe going after somebody. Okay, so then again, we're gonna draw this line relative to the dragon and parallel to the ground, and this is 30 degrees right there. So it's, if you look at my hand is either with the horizontal 30 degrees above the horizontal or 30 degrees below the horizontal. Okay, so that's what that means. Okay, so that's talking about something moving up and down, side to side. Let's go down to what happens if you look down on something, like a bird's eye view. What that looks like is, imagine you have this dragon. He's kind of flying above this knight down here on the ground below, and this knight can move side to side, north, south, east, west. This dragon is looking down on him from a bird's eye view, so looking down on something. Okay, so let's draw what that looks like. You have an eyeball. And you're looking at something moving on the ground in all sorts of directions. Okay, whatever that may be. That's the plane of movement. So the plane of movement is parallel with the ground. So that's what that looks like. Okay, let's do an example together. So we have here a lost kitten. Let's draw him here. Okay, you have a lost kitten is going to walk 3.4 meters south and then walks 1.2 meters west. So that's a little shorter. We can draw a little shorter arrow. 1.2 meters west. Calculate his total displacement. So when we calculate the total displacement, remember we always draw an arrow starting from the starting point, and the tip of the arrow ends at where the kitten finishes. So that's our total displacement. Okay, so then I'm going to write that as a symbol that you will find in your data booklet, which we will talk about later, which is S. And don't ask me why it's S. It's what the data booklet dictates. So some of you might see it as D instead of S, but it's just a letter. Let's get over it. Okay, so we're trying to find total displacement S. So because this is a vector, we need both a magnitude and a direction. So let's start with the magnitude first. That seems to be the easiest to work with. Let's use purple. I hate that purple. Let's do this purple. Okay, starting with magnitude. Well, I mean, this is a triangle, and we've gone over triangles at the beginning of this unit. So let's start with finding this magnitude. If we know two sides of a triangle, to find the third one, notice that this is a right triangle because the south and west are directly perpendicular to one another, 90 degrees. So we use the Pythagoras theorem to find displacement. That is c squared equals to a squared plus b squared. Just write that up here so you remember. Equals a squared plus b squared, where c is the hypotenuse. S is your hypotenuse. That's your total displacement. Okay, so then let's substitute everything into our Pythagoras theorem. So we have S, and that little arrow up there, sorry I didn't explain this earlier, I use that to denote that this is a vector and not a scalar. So that little hat looking thing that looks like a half of an arrow. So we have S squared is equal to one side of the triangle 1.2 1.2 meters squared plus 3.4 meters squared. Okay. So we're going to calculate this first. Normally I would have done this all in one step, but I think we'll need to break it down a little bit. So let's do 1.2 squared plus 3.4 squared. That gives us 13. And I'm going to put square here. Technically the units are also squared. And that's displacement squared. So now how do we get rid of the square? We take the square root of both sides. Aha. So this gives us our displacement is, take the square root of 13, or on here you can just use the answer 13, 3.6. And if we round it up to two significant figures, that's just 3.6. 3.6. Now the units are also square rooted, so we are left with just meters. So now we have the magnitude. Next up we have the direction. So the directions, this is where it's going to get a little tricky and nuancy, but let's get started into that. Okay, to show the direction, we can't just say south and west, or southwest, or west-south. Something that you may have heard or seen before. The reason why is because if I say southwest, my arrow can be pointing in this direction, which is also southwest. This direction, this direction, this, actually not that slanted. That direction, we don't know in which direction. We have to be more specific than that. And this is where we need an angle. So we need an angle and some combination of the words south and west. And the angle that we can try to solve for is, I'm going to use this one because that's our triangle. And we have our triangle laid out, our right triangle laid out. We learned about trig. So let's get started with our directions. Okay. So this is the angle we want to look at. I'm going to label it with theta. Okay, so let's take a look at what we can use. We now have all three sides. True that. Now the question is, do we want to use 3.6, the answer that we just found out, or would we rather use the numbers we were given? What do you think? Take a moment to think. So, for future reference, it would be preferred if we used numbers that were given in the question. Why? Well, let's say you made a mistake in calculating 3.6. That means you would use the mistaken answer to calculate something else, which then would make a mistake in that as well. So you're carrying out the error that you've started off with. Always better to use something that you're more certain of, which is what's given in your question. So I'm going to use 3.4 and 1.2 meters as the side angles to help me calculate this angle here. Sorry, the sides to calculate my angle. Now look at our triangle. We have here the blue line. This is our hypotenuse. Okay, we have this side of our angle, which is our adjacent. This opposite side here, 1.2. So if we have adjacent opposite, what do we have? A and O. SOHCAHTOA, TOA. There we are. So we have A and O. That means we need to use TOA. Okay, that's tangent. So let's write out our tangent equation. Our tan theta is equal to our opposite over our adjacent. This is 1.2 meters over 3.4 meters. Okay, so let's write this out neatly over here and I'll calculate this. That is 1.2 divided by 3.4. Not a very nice number, but we just got to deal with it. 0. And if you can save these numbers in your calculator, the better, because it will be very precise for you to calculate whatever's coming up next. So I'm just going to write 0.3529. 29 dot dot dot. And whenever I write dot 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 means I wish I could have saved all those sig figs to use for later. Okay, so then write that tan theta equals 0.3529 dot dot dot. Now, how do we find the angle again? Well, if we have the ratio, yes, inverse. So we're going to use inverse tan. So theta equals to tan inverse of 0.3529 dot dot dot. Okay, so let's see what we can do. Now on your calculator, I'm not sure if you have this function, but if you do have a graphing calculator, you can easily use this. So we need the inverse tan. Second tan gives our inverse. Now how do we take that number up here and how do we insert it back in? We can use second, and down here this blue thing says answer. Press that button, bracket it. Okay, sorry, should use my mouse here. So here, second answer down here gives you the answer that you just got previously. Close your bracket, enter. Oh, we got to check. Remember, that's very weird because usually the graphing calculators that I open should save everything. Okay, there you go. Sorry, let's see. This is something that you should always check if your calculator's in degree mode and not radian mode. I thought my calculator remembered that, so let's do that again. Guess it didn't. 3.4. There we go, 19.44. We're just going to round it to 2 sig figs, 19. So we have 19 degrees. Okay, so this part, finally, we get to talk about how do we write down the directions properly using an angle. So we can't just write down willy-nilly 90 degrees southwest. That's still not specific enough because I could be talking about, let me write it in black. Am I talking about 90 degrees relative to the west marker? 90 degrees here? Or am I talking about 19 degrees from the south marker, right? So we need to be more specific. So how do we write this down? We're going to look at how this angle was formed. So to get this 90-degree angle, we first went south, then we went west. So we are going to write, and I'm going to explain this again, 3.6 meters, 19 degrees. We start with the angry. Yes, I am angry. Start with the angle, 19 degrees. This is where it gets very weird. West. So notice I don't start off with south. West of south. Why? Why? Okay. So the key thing here is this word of. Okay. Though it's west of south. So using our linguistic skills, intuition a little bit, or skills, or whatever you want to call that, which one is more important out of these two words? It's west of south. So it's saying west of south. West is describing south. South is the most important word here. So if west is describing south, south goes first. Okay? So, actually, let's use this. South goes first. So, south is first. And then we go west. Okay? So, south, west of south is, west is describing south. Therefore, we go south first. Another way you can remember this is whatever the order that you took to make your triangle, you reverse the order of the two directions. Okay, so if you went south, then you went west, then is west of south. You just flip it. Okay. Now, yes, it is really weird, and it does have something to do with this word of, and you just got to get over it. It's the opposite of what you would think. Okay. Now, some of you little cheeky youngsters might be thinking, well, what about if I made my triangle this way? Okay, so if you did that, that was totally fine, because it's still describing the same direction, except you went west and then you went south. But here's the caveat. If you had done that, that means you would have had, let's use this, then you would have had this angle instead. Now, is that angle 19 degrees? No. But what is the relationship between this orange angle and the green one? Yes, they are complementary to one another. Okay? So, if you want to find the complementary angle of 19 degrees, what do? And yes, you do. Take 90 minus 19 degrees. You get 71 degrees. If you don't trust me, check it with your calculator. Okay? So now you have 71 degrees. Okay? That's not wrong. But now here's the other thing. You can't just say west of south, because we're talking about a different triangle. This triangle, we go west first, and then we go south. So that means we got to reverse the order, meaning we got to say south first, and then we say the west. So south of west. So if you flip the angle using the complementary angle, then you also need to flip the two directions. Okay? Whew! Alright, so that is tricksy. Tricksy. Okay, so let's nail this home with a few more examples. Now, I just did the one example with south of west, so that's just using how to make, let me just make up this example that we just finished. South of west, if I had to draw this one out just to copy what I did up there, then I draw west first because that's the prime, that's the important direction, because south is describing the west. We flip the order, so that's first, west, and then we go south. Bam, okay? And then the angle is whatever triangle that we have. This angle from our starting point to our ending point. So that's 71 degrees. Let's quickly look at a few other examples, like this one over here. Let's do, I don't know, 62 degrees east of north. Okay, so let's draw north first. So we draw north first, then we draw the east second. East is this direction, and then the triangle that we make right here is 62 degrees. Let's say we said instead of 62 degrees east of north, what if we have 62 degrees north of east? Then we start from our starting point. Oh, maybe we should move that a little bit down, like here. Starting point, let's go east first. Remember, it's the opposite, east. Then we go north, okay? This triangle that we make right here, this angle, that's 62 degrees, okay? So here were a few examples. Okay, so before I do the last example, which I'm going to give you a chance to try, of course, let's do a quick recap. Okay, so we talked about directions. 1D direction languages, and then 2D dimensions. 1-dimension languages and 2-dimension languages. The first dimension, we only need to deal with one straight line, either north, south, east, west, up or down. But with 2D, we have to think about directions that could potentially be on a plane. So if you're talking about up and down, something can be moving up and down and then left or right. Okay? North, south, east, west included, but we're not going to do 3D. That's university. Good luck with that one. It's fun. It's awesome. So there's that. The other one is looking at 2D, where the plane of movement is parallel with the ground. So what that means is your eyeball is in the sky and you look down at whatever is moving down below you, and you're describing the motion in 2D north, south, east, west, but using an angle as well. Recap on using the angles, okay? So whenever you say some angle, if you say some angles, something, one direction of another direction, it's always the opposite of the order of what you think it is, okay? So you flip the order, and that's how you would write it, and that's how you interpret it as well. So I go 90 degrees west of south, I take my marker, I move south first, and then I move west, okay? So it's always the opposite. Okay, we did some examples, and now here is the last example. So what I'm going to do is I'm going to give you a chance to try yourself after I explain the question. So here we have a lost kitten's sister. So that was just from the previous example, the kitten from the last example. So this sister moved 8.7 meters north and 2.5 meters east. Calculate her total displacement. So very similar to the last question. Okay, here's a good chance to pause the video, try it yourself, and I will play the rest of my solution video in fast play. Okay, here the fast play will begin. I'm going to be shifting angles, turning off my mic so you can watch this in fast mode. Alright, so here we have it. Here are our two potential answers if you did the triangle in the opposite direction, or the other angle, which is this triangle over here with this angle down over here. Okay, so 8.1 meters, 16 degrees east of north, again using that language where we reverse the directions, and then 74 degrees north of east if you're using the complementary angle. Alright, so great job bearing with me through this video. Good luck with your examples and doing some practice. Fat Mama Physics, signing out.